Right, I think I'm live on YouTube now. Need to set up a couple more items and then okay, I think I've got the YouTube video properly set up. Hi. Okay, I need to invite the people on Discord now. Oh, I also should drop a Discord invite here on the channel again. There is the Discord invite. Now I need to invite people on Discord. There, I think I've got the Discord people invited now. Oh, what do I follow? I actually have a resource that I made for I'll post a link to it. I've got like 20 books on system design though. Here, I'll show you. It's I made this picture about system design. And I actually have almost every single book on here. I think with the exception of that, I've got an electronic copy of it. It's not good. I mean, it's not bad. It's not like the worst thing I've ever seen, but it's kind of like the old school early 2000s definition of software architecture, which is where it's like literally coding instead. But I should post a link to this in the YouTube channel. Yeah. Can the streaming resolution be 1080p? So I currently have my resolution set to 1080p. You might just have to click on the settings on the video. I think I've seen some comments before about the streaming, about the resolution of the video. I've got it. I've actually, let me click on video settings. Let's see if there's anything that I can change. I'm like running the live stream off of Zoom though. Oh, I don't have the Zoom chat open. That's bad. I don't see any comments from anyone though. So no huge issues. But yeah, I actually run the live stream off of Zoom, and I should probably switch over to OBS instead. That would probably be a good idea. But I'm just not really on top of things in life. So I'm not using OBS. But I think if you try clicking on the settings of your own, like on YouTube, you might be able to improve the streaming resolution. Like there should be like a little settings option on the YouTube menu. That might help. There's actually one more resource I need to add to the resources list over here. I know there's this Russian guy that literally runs literally the System Design Interview YouTube channel, and like his most popular video is the top K problem, I think. And I haven't actually ever gotten around to watching it, but he seems to have a large following. There's a lot of fans of him. Um, and this guy, he was an L6 at Amazon. I think he went on to be, whoops, coverage from these. So he was an L6 at Amazon. I think then he became staff at some other company like Stripe or Square or something. But he's a solid engineer. And I mean, I've just never really gotten around to watching his content because I really like books, which is like hypocritical seeing that I run a YouTube channel myself. But yeah, I heard his content's pretty good. Okay, I need to get a couple of things. So I'm gonna go quiet here. Feel free to post any questions in the, yeah, it's Mikhail. I think his name is Mikhail. Um, shoot, does he actually have a link to his LinkedIn? Yeah. Okay, I see his LinkedIn on his channel. Mikhail Smarshov. Yeah, thank you. Yeah, his name would probably be a good idea to have there instead of just his YouTube channel name, because his YouTube channel name is just literally System Design Interview. And like if you actually tried to type that in, I mean, there's a few dozen people that are probably covering it by now, and his has a very generic name. And so it's like, yeah. I was surprised by how little coverage there actually was on this problem, though. Okay, give me a minute to get a couple of things. I'm going to mute myself, but we'll start at 10:45. Okay, I think we are good to go ahead and get started. I'm going to kill this window. Um, so, all right, today we are going to be covering the Spotify top K songs problem. I just kind of wanted to cover some kind of top K problem, also known as the heavy hitters problem, or at least that's the name that Mikhail gave it to it in his YouTube channel. There's only one other person that had kind of solid coverage on like exactly this problem, which was Stanley Chiang in his book, which is called Hacking the System Design Interview. It's actually decent coverage of this problem. It's actually pretty good. He actually kind of goes into depth on how Countman Sketch works a little bit. I don't like it when people go into too much depth on Countman Sketch because that's like component internals, and that's like getting hung up on implementation details instead of just how to leverage a component. And then Don Martin actually like documented the problem. His solution doesn't use the best components that I'm aware of. I think he just uses a SQL database, and that's not really the way to go here. And then Alex Shu does do some stuff with Countman Sketch, or like some kind of streaming analytics problem in ad click aggregator, or maybe it was the metrics monitoring one. Stanley Chiang went a little deeper. Like I said, he went into Countman Sketch a little bit. But I think and Alex Shu also did not explicitly do top K problem. It just is like nice problems that also use streaming analytics solutions. And then again, like I said, Mikhail also covered this problem. I'm not as familiar with his videos, unfortunately. I really like written content myself, which is a little hypocritical, of course, since I run a YouTube channel. But I've heard a lot of people say good things about it. So anyways, the requirements. So you're going to be, you want to show the top K most played songs in the past 24 hours. I think Spotify top K songs is the most common prompt I've seen for this style of problem, but there's a lot of really similar ones, like the sales rank one for Don Martin's primer. So you want to show the top K ones, and then well, so you're also going to be recording the songs as they're played. So record and count the songs as they're being played by end users. So technically that's a requirement. You can summarize the whole thing with that, and that's like the gist of things. We'll see if I can actually remember to do my checklist this time, and live discussions here. Any questions before we begin? Okay, all right. I'm going to go ahead and hop into doing the diagrams, of course. So I can start off with the naive solution, which is the mapreduce approach. That's a little bit more popular, or like for people that are completely new to system design, it's really common to see a mapreduce approach. So you would have Spotify app user playing a song. And then you'll have some kind of analytics service that's collecting that it's hit whenever you play a song. It's the analytics collection service. So maybe you could even just batch send logged plays, but you're going to be having these recorded instances of playing a song. And then you're going to need to record that somewhere else. It's going to hit storage somehow, but let's cover all the entry points and exit points before we dig into that. So we're going to have the Spotify app showing top songs. Going to need to get that from the song listing service or something like that. Right, so you're gonna have some kind of service that's going to be doing reads though, and you'll be doing a read off of that. Okay, and then the naive approach. So you can do, I mean, the most naive thing is where you just have a regular OLTP database. You could use something like Cassandra, is I think a really popular. Well, it would make the most sense in the naive approach. So this is actually like the approach that I would have done like about a year ago. Is that you have the plays, song plays data source. Every single instance of a song getting played, you would have a record getting written over here. And so this would be write heavy. So you would think, this is some kind of it's an OLTP use case. It's write heavy. You're storing a new record for every individual song play. And that would make sense for other analytical purposes like song recommendation. And so then you would think, and then of course the optimal data store for that would be Cassandra. Chooses an LSM tree, eventual consistency, stuff like that. Cassandra even has nice integrations for, I think, mapreduce, because they're both part of the Hadoop ecosystem, I believe, or they're at least both out of Apache. And so it does actually have nice integrations for mapreduce. And so you might be thinking of doing mapreduce workers. And you would, let's make this a little bit larger so that text isn't all screwed up like that. We're going to do two different naive approaches, actually. There's another slight improvement that you can make over this one. So you've got all that, and you just want to sum up all the instances of it. Let's do a schema really quick. Is that you would have, so it'd be song ID 1, 2, 3, 4, and you'd want the timestamp 70005,000. Okay, and so then you would just kind of pull all the records from the last hour or something. You'd sum them all up, and then you might stick them into some kind of cache. And this would not be real time. So this would be like once an hour you would update it. While the problem is going for real time top K songs. I should actually specify that. So if you want it to be updating in real time, that makes it a lot harder. As in, like, if something spikes a ton in the last 5 minutes, it should start showing up immediately. Anyways, we'll have a cache of, it would be like the results cache. Maybe use something a little more durable even, but we would also put a caching layer in front of it, even with the durable layer. But you'd have some kind of cache, and then you would, of course, pull from cache for the listing service. And then the issue with this is that you don't get it in real time. And then also you are doing MapReduce workers against a OLTP database. So let's go ahead and I'm going to go ahead and show what I'll list off what makes it naive. So MapReduce on Cassandra on your OLTP database is a no-no. Don't do that. Also, this is not real time. It's discrete hourly updates or something, or some other frequency. You might be thinking just pump up the frequency to like once every 5 minutes. And I mean, that helps make it a lot more real time. And the fact that we have it at 24 hours would really help with justifying that. But if you crank that down to like an hour or something, or the last half an hour, it's you're still kind of doing it's you can get more real time. You can make something even more real time than you can accomplish with MapReduce. So it's you're shooting for real time. Okay, what else is the issue here? Is there anything else wrong with this? I think those are the big ones. I think those are the big ones. Yeah. Let me know if you have any questions about these issues with the approach. I'm going to cover a slightly better approach. And then yeah, okay. So we're going to do a slightly better approach, which is just that, just addressing the OLTP part. So doing slightly better than this is that we at least want to have the MapReduce run against an OLAP table. So the issue that happens when you run against an OLTP database is that you're going to get this big latency spike against this thing whenever you do that. And you don't want to have a big latency spike hitting that thing. That would impact, I think, possibly the speed of the writes hitting, but sometimes you have an OLTP database that's shared for writes and read data. In particular, when you're also doing reads off of one of these, I think that's a huge, you really do not want to have any MapReduce jobs run against an OLTP database that's also serving external reads. So we got this OLTP database, and all we really need to do to slightly improve that is that we're going to slap a OLAP table between them. We want to have this, we want to do change data capture. We're going to have an OLAP database. So this one is OLTP. Still, that's fine. You can capture it in an OLTP database. That's fine. But the issue is that you don't want to do MapReduce directly on that OLTP database. So then we're also going to have OLAP. This is the data warehouse. So at Amazon, my own team actually would we actually had these DB triggers set up where it would just send it off into this like stream. You could even decouple these two things with Kafka. We would shoot our data into Kafka, and then somewhere downstream from us, there's this data warehouse that would consume off of it. But you might even be able to just do the DB triggers directly into the OLAP database. And this is something like, it could be Druid, it could be, I think Redshift is one data warehousing solution. But what you want to do is change data capture. So that's, you can abbreviate it as CDC with DB triggers. And that's what my own team at Amazon did with one of our solutions. I don't like how it was, how the text looked like that. There we go. There we go. Now I'm happy. All right, close enough. Okay, so this is slightly better because now you're not running your MapReduce job directly off of your OLTP database. You won't have those huge latency spikes that could be visible to your external users. This is already a little bit better, but you still don't have real time. And so, a natural approach is like, hey, you might try and do, you might just try and like crank it down to every 5 minutes, but still that's not real time. That's not truly real time. So we've solved that issue. I think, can I do a strike through? Am I able to do a strike through in? No. Yeah, okay, that would have been sweet. Yeah, okay. Just checking questions on the chat. I think this is a good time to go through that a little bit. Let's see if anyone's confused by anything. Okay. Oh, there was a different thing that I wanted to. What is CDC with DB triggers? How does it work to send OLTP? So CDC just means just change data capture. There's a little blurb about it in DDIA has some content on it. It just means change data capture. It's that you have this concept of a source of truth or a system of record. It's the initial place where you capture data. And then you might pass it downstream into these, you might have like a read optimized view. That's actually a concept that is kind of discussed in DDIA, is you might have read optimized views, and then you'd have this like write optimized database, like Cassandra's a great example of that. And then you would like do a DB trigger on the end. So a database trigger is just built into almost every database out there. Elasticsearch does not actually have database triggers. And in fact, that's possibly by design, is that you're actually not supposed to use Elasticsearch as a source of truth or a system of record. That's in their documentation not to do that. So that would be like a forcing function to not use Elasticsearch as a system of record, to just not build database triggers into it. But otherwise, most databases have DB triggers. So for example, PostgreSQL definitely has them. DynamoDB has them. I would be shocked if Spanner and Cassandra don't have them. So they should be in there for those ones. And then how does it work for sending from OLTP to OLAP? So it's just like this thing that happens. It's I think usually it's like subscribed to your write ahead log or something. Yeah, I think actually even DIA might have talked about the Bezium, I think is what it's called, which is this nice plugin into something that is like optimized for change data capture purposes. It might be for PostgreSQL, and it's just like it's just really good for that use case. And but anyways, you just have this database trigger. Whenever you do a change to the database, you update a record, you write a new one. It's this thing that fires at the end that allows you to then run some custom code. It might have you like then do another update to the same database, or you can even use it to then have it like interact with stuff outside the database, kind of like an API call. You'd have it then call external services, as in like call stuff that's not in the database itself, just like other machines. So it's almost like running server code in response to database updates. It's a thing. It's just like this thing that your database runs that reacts to whenever you make a change to your database. And so then you can use that you can either send it directly over there, or another approach. I'm going to go ahead and draw the diagram for this other one that I was describing, where it was more similar to what my team was doing at Amazon, just where you had this this stream that was between the two. So I had it like that, and actually decouple them a little bit. And that would actually make sense, particularly in the case of a data warehouse, because it'd be a different team. And having such a close coupling like that, it would only make sense if it's somebody that's like on the same team. Let's do that. And this is going to be a broker like Kafka. In fact, let's say it is Kafka. So we're going to say message broker Kafka. And then the broker itself doesn't push. So you actually need to then have some task runners that would copy. So you just have use I think it's called Lambda triggers, AWS Lambda triggers, I think is what it's called. And they can just it's just like a Lambda function that you can use just for pulling straight off of Kafka, and you would use that and it would push the data into your OLAP store. So you just use it for turning a pull into a push, because you have to pull off of Kafka. Services don't do that. Services do a push. So you would have to use, so like triggers are probably the easiest way to set that up. I know there was a lot of stuff recently about how serverless is very cost ineffective, but I think Lambda triggers are just like the easiest, lowest operational expense way to set something up. It's easy. It's just easy to do. But so that's what I've seen at my old team when I was in the retail org at Amazon, is that we were like this chunk of the infrastructure, and we had this pipe just where we dump our data for downstream stuff. And so then somehow somebody downstream was pulling off of it and shoving it into the data warehouse. Yeah. Okay. And let's try to do that today. That would be cool. Yeah, we can try and do that today. I haven't done those. I've really sucked at those lately. Oh, you know what else I forgot about? What's it called? Load balancers. We should maybe throw some load balancers in here. Yeah, let's maybe just do that right now. So I think these are probably this one's particularly going to need to have a load balancer in front of it. I think unless you're bulking up the logs, you're handling the logs sufficiently big enough batches. But I don't think that it's really the norm. Or I mean, yeah, I don't think you're going to be able to. I don't think you can reasonably batch them up in such a way that you're not going to still need to have a load balancer there. So you can just apply what I've just done to the other two diagrams. We're going to keep moving on. And we can do total number estimates at the end. Hopefully I'll remember to do that. Any other questions before we keep moving on to, I have one more naive approach, and then I'm going to cover the streaming analytics approach. Okay, we're going to do one more naive approach. This one actually was explicitly mentioned by Stanley Chiang. I'm kind of stealing it a little bit from him. It was really, his book was great. I'm not going to explain count min sketch like he did, but his book is actually pretty great. You can only get it as a physical copy, unfortunately, but I think it was pretty good. So this other one that he wanted to, that he kind of covered was some databases support CRDTs. So you can do, you can just go ahead and have it count up. You would just have like the counter right here, and then it would be like 5, 6, 7, 8. And you can even then use, so if you're doing hourly, you can have hour bucket. So you'd have timestamp, hourly timestamp bucket. And so then it would just be, you just use the floor function, use the floor function on, you have, what is it? There's like 100,000 seconds in a day. So you would just have, it'd be the timestamp divided by 100. Oh, it's 86,400 seconds in a day, I believe, and you divide that by 24 for the number of seconds in an hour. In fact, let me maybe just kind of like spell that out a little bit more. So we'll say seconds in, seconds in, and hour. So you just divide timestamp by number of seconds in an hour, and you're just running the for function over top of that whole thing, and that gets you the hourly timestamp bucket. And so you're just kind of like using these as a key, and then you can just use like Redis, which has a CRDT for counters. So Redis, leverage the counter CRDT, specifically a grow only counter CRDT. And so then you'd have something that looks kind of like that. And it should still be write heavy. And then you're incrementing a count. You're incrementing a counter for every individual song play. Still is an OLTP use case. So you would think that's good, but he said that it still works kind of like mapreduce. It's also, so you can get a double counter issue also when you're using Redis, is that, so if you do the count and then it gets a drop on the return from Redis, then it would, you would then have like, the server would not know that it successfully wrote. So there's another CRDT called a, shoot, I already forgot the name of it, but you're actually able to use a deduping ID to prevent it from doing that double count scenario. But I don't think that CRDT is the norm for how counters are implemented. But in we also don't care about exact accuracy for the count. If we did, that would actually make it even more, I guess that's even a variation of the problem that we can even get into more at the end is if we did care about the exact count, but in the account, we don't actually care a lot. We don't need an exact count. So that's usually the variation done for this problem when you want real-time data. If you want an exact count, you are kind of stuck with doing mapreduce jobs though. Anyways, so it does have that issue with CRDTs still, but you don't care about exact accuracy, so you can kind of hand wave that away. And then also with how we're setting up with the buckets, you would be resetting it at the top of every hour. So that still doesn't work perfectly. You are able to get rid of the MapReduce workers completely. And then you are just going ahead and reading straight off of the song plays data store. But it doesn't actually get you, it like resets it at the top of every hour. And so then, I mean, I guess then you could use a couple of, you could do an approach where you're reading off of several buckets. And so if it's 24 hours, you'd have like 23 that are complete. And then you would be just killing the oldest bucket every single time. And then you would take like the newest one or something like that. But then it still is not like truly the last 24 hours rolling. The end of it would be rolling, but then it'd like drop off every single time. And so then you'd get this like sawtooth pattern to the count kind of for the top songs. I think there's some kind of other issue. I think he argued that using Redis for a counter here is just kind of reinventing MapReduce in a way. I think it's kind of clever and it does kind of work a little bit. there's definitely some issues with this approach though. There's a better one out there. So this though, it's naive approach 3. I actually think it's kind of clever. I do actually think it's kind of clever, but it still is not really the best solution that we can do here. So still, it is very clever. It is very clever, and I do like it. It's real. It is real time on the end for the end cutoff, but the start time is still not quite real time. Yeah. Okay. Yeah, okay. I guess we can move on to our last approach. I'm going to copy what I did over here, so I don't have to do as much drawing. And then I lost my load balancers. I got to add those back. I think I can copy those off the one I just drew again. So just do that. Okay, and now we're going to go over the real-time approach. So I think you can even just throw out the OLTP completely. You can just go ahead and have a stream actually. So we're going to bring out the Kafka stream again. So we are still going to have a message broker, Kafka. And then another cool thing about Kafka is that about having this broker in here is that you can also have it read off into a different thing for analytics. But what we want to actually use is this kind of arcane component. It's a streaming analytics solution. So you can use Flink, or you can use AWS Firehose. I think what another one of them is called. And then I think there's even Spark streaming, Spark streams. There's some kind of thing in Spark that can handle streaming analytics. I think it actually does something called micro batching. And so it looks kind of like MapReduce under the hood. I think it should still be running. I actually don't know if it does min count sketch or not for Spark streams. I would imagine that it's doing min count sketch, but I heard something about micro batches for Spark streams, which is the idea of, so it's like, okay, so if it's just doing MapReduce, then that's taking the idea of doing just really small increments of MapReduce and just doing that to an extreme, micro batching. But the first two are doing count min sketch, which is the most commonly, it's considered the most correct and optimal solution to this problem is doing count min sketch, which is explained a little bit in Stanley Chiang's book. He does actually kind of explain how min count sketch works in there. You don't actually need to know exactly how min count sketch works. If you're applying for like a staff level position or something, maybe it would make sense to actually know the internals of it. But you can clear mid level and senior just fine without knowing the internals. Anyway, so this thing I believe is going to pull straight from your stream. It'll pull straight off of the stream, and then it does some kind of analytics internally, and then I believe you can query it directly. So you send a query straight to that, similarly to just like it's a database or something. In fact, there's this thing called KSQL, and I heard it even has like tables or something, or you can even do transactions, or there's like this like KSQL two-phase commit thing, just weird stuff that I would not expect to have performed on this kind of solution. but it just shows that you can treat it a little bit like a data store, although that would be a very incorrect way to actually think about it. But you're just doing a query off of Flink. So I'm going to draw that another way is like this. That way I can be unambiguous with who's making the call request here. Okay. Yeah, and then I can draw what I was talking about here with how this is still also very convenient for analytics and stuff. Is so in messages, you can still have it set up in such a way where you have song ID is like 1, 2, 3, 4, and you can even have the user ID in there. So we can have my one on Discord. We'll say that it's Ubidesu, and then we'll have what else do you need on there? Timestamp, sure. Have the timestamp 67000 5000, just like that. You can still have that as the message, and then it gets aggregated by Flink. But given that you have the user ID in there, you can also have a different consumer where it's running, where it's doing analytical stuff. We're figuring out song recommendations. So you can even have some kind of other task runner. So a Lambda trigger. And you can have that pull off of Kafka. And you can have it write over to a data warehouse. So it's just copying over to a OLAP, similarly to what we had over here. So we're just copying this little piece, just this chunk. It's like taking this and then also having another thing for the Flink component. And then also we don't have the OLTP there. We can actually stick the OLTP on the other side. And then if for some reason you needed to read directly off of the OLTP, then you would be getting eventual consistency, and it would be a perfectly valid solution, I think. Anyways, let's go ahead and actually copy that OLAP store piece from over here so that I don't have to type as much. There, and then so it's going to pull the data off of Kafka, a whole batch of 10,000 messages at once, I believe. No, is it 1,000? Yeah, I think so. I think that you do a read of up to 1,000 messages at a time off Kafka. You can do that 10 times per second per shard to pull in your batch 1,000, and then you paste it all over to your OLAP store. And then you can do other stuff over here for figuring out song recommendations. So that's another advantage of having that Kafka broker over here, is that you can have multiple consumers off of it, just like that. And you know, I'll like box up this to like show like that's not actually part of the what you actually need to say in the interview. It's just me elaborating on other contexts that you can have in like real world systems. But this is considered like the most optimal approach. There are no correct answers in system design, only trade-offs, but most optimal, it's widely considered the most optimal. I have little quotes on there. So you can imagine me doing air quotes with my hands when I say most optimal, because I don't like thinking that there's a correct answer to anything, but it's widely considered to be the most optimal approach. And I had told somebody we were going to do server estimates, so we can go ahead and do those. Any other questions before we move on to that? Okay, let's go ahead and do total server estimates. All right, so we need to have some kind of write TPS. We need to have some kind of read TPS. So let's say that we have something like I don't know, 50,000 writes per, we'll say we have 100K writes per second. Okay, we have 100K writes per second coming in over here. So figuring out how many server machines you would need is really tricky. Is it bandwidth bound? Is it CPU bound? In this case, it seems like it's like connection bound or something like that. I've actually never seen a machine in my own services that could handle over 60 TPS. And so with that impression, you would think that you would need like 1,000 machines over here. So I had mentioned that you could use logs or something to batch up the writes, and that would maybe be a really good idea. So let's say that there's 100,000, you could say 100,000 songs played per second. And then let's say that we batch up 100 seconds, 100. What if we do, yeah, let's say we batch up 10 songs at a time. Batch up 10 songs at a time in the logs for passing over to the service. So that would cut it down to 10K writes per second. And I've still only heard of like maybe 60 TPS on a server max. But I know that if you use Erlang or something like that, you're able to get up to like 100,000 concurrent connections per machine or something. So I'm gonna say that like maybe just because it's just not doing a ton of stuff, you like maybe have optimized the code over here to handle a much higher load, and you can handle let's say 1K writes per second per machine. So I'm going to say that we have 10 machines handling this. So we'll say 10 machines total. I forgot that it's probably going to be globally run. It's probably going to be a global service. You're playing Spotify worldwide. So this is 10K across the whole world. And let's say that we're going to split it across the Americas. So we would have North America, South America, and we're going to have Europe as another big zone. We'll have Asia as another big zone, Asia plus Australia. So we'll say 3 big zones, and then we're going to say that we get maybe we'll say that it's even across all 24 hours. I mean, of course, you're going to get a peak, and so we'll say that maybe it's 4K. We want to handle 4K to 5K writes per second in each region, and not scale it up and down within a single 24-hour time period. I haven't really seen that done a lot. I know that auto scaling is a thing, but I haven't seen it done in practice a whole lot, actually. So usually usually what I've seen is leaving it scaled up to the peak for the whole 24-hour day. So we'll say, let's maybe handle 5K within a single region. And like I said, let's say that one machine can handle 1,000 requests. So it's 5 machines per region in 3 regions. And I have never seen estimates for Kafka. I have 0 practice with that. I did mention that for doing the reads off of it, you can handle 1,000 messages per read 10 times per second. So you can handle 10,000 messages per shard. And we were doing 10K writes per second. We could split those individually so that it becomes, so within a data center, you're going to have much lower latency than over here. This area over here is going to be very high latency because you're going from end user to data center. So that's going to be like a 1 to 2 second latency. While when you're within a data center, you can pull sub 100 milliseconds a lot more easily. Yeah. So I'm fine with splitting it back up and doing individual messages because they should happen a lot more quickly. But I don't know. I don't really want to do estimates on Kafka. I'd imagine you'd probably need about the same number of machines. I don't know how a shard, I don't know what the heck a shard is in Kafka, if that's like a couple of machines or if a shard is like one individual machine. But I'm going to guess at least 3 to a shard. I'm pretty sure that you can handle that volume off of one shard. There's no way that you would need more Kafka machines than you would need for this. Kafka does direct memory access for the writes, DMA. So the writes should be really fast, and then you're doing these batched up reads off of Kafka. So it shouldn't, I cannot possibly imagine Kafka needing more machines than you would need for this. And then Flink is doing those batched reads off of it at 5 reads per second of 1,000 messages or something. I've also, yeah, that would suck for doing estimates on. Okay, and then I don't think, so people are going to be doing a lot more listening to songs than looking at the top K songs. You're not going to be looking at the top K songs nearly as often as you're listening to songs. So I think we can go ahead and say maybe 1 KTPS for listening service. And we'll say that it can handle the same volume as these, 1K per machine. So, and again, it's worldwide. And you should do N+1 per region. So although you can comfortably handle the volume with just one machine in each region, it's a good practice to have N+1. So we'll say 2 machines per region, 3 regions. Yeah, and then you wanted estimates for the database. Yeah, well, so this one's going to be like storage bound because that's analytics data. And then that one's actually out of scope. But if you were going to do estimates on the OLTP, I can do machine count estimates for this thing. Yeah, I can take a shot at that, and then I'm going to hand wave away the latency. But like if you're going to do machine count estimates on that, this one would need more machines than the cache. The cache is also going to be, let's go ahead and copy over the machine count estimates from our use case over here on the right. Is that we had this, we had this. Yeah, let's copy those over to here. So those should still be accurate, I think. And then I want estimates on, I can do this one first. It is lower volume. I'll go with this one first. And then, so this one is maybe Redis. And again, that should be able to handle the volume much more easily than whatever the heck this thing is doing. But you're also still going to have N+1. You would just have one extra machine just for redundancy in case one of the machines has some kind of random outage issue. If there's some kind of random transient issue or just data center weirdness with one of them, you would have the extra one for redundancy, so you can still handle the traffic volume comfortably with whatever else is there. And then let's do this one. Okay, you can definitely handle at least 1K transactions per machine. I've heard some people say you can handle up to 10K off of a single machine. I think that's wild. Let's say that one machine can handle 2K for Cassandra, because yeah, people definitely say that you can handle 10K with Postgres or RDS, but I think that might, you don't want to be pushing your machine straight to the peak limit in prod, because then you're kind of playing with fire and you're playing with risk there. So let's say that we're going to do 2K transactions per machine on Sandra, even though 10K should work. And then we're going to be handling I want to do that. Okay, sure. 100K songs per second. We'll say this one splits it again out on doing the writes, or I mean, you can do a batched write operation. You can do a single call over that has, so if you're doing the logs and you're sending over a log of 10, I mean, you can just keep it as 10, and then you just do an insert with 10 records in it. So it would be a batched insert of 10 records. So then you would do a 10K writes per second of 10 records per write. Okay. But that's, 100K records per second. You need 50 machines. I don't like to think that I would actually need 50 machines for this. That's a lot. I've never heard of needing 50 machines for something. Discord actually runs off of 72 machines for SkylaDB. So a comment in chat. Top key songs are personalized per user. Bringing in more parameters like users' previous lessons, etc. Can we talk about how and where to club all data in most optimal approach? Well, so if you have that other data, that would be in the data warehouse. So that would be over here and it would already exist somewhere else. And so there would be like big, expensive analytical queries happening every so often, but it's in the OLAP table, so you're fine with that. Yeah, so you'd have like other data sources that are populating data over into the data warehouse. And so if you were trying to do big analytical queries on an OLTP database, that would result in latency spikes. But since this is not serving any, you're not relying on this database for serving low latency queries off to end users. So it's fine to have those big analytical queries over here, and you're just sending it all over into that. And I mean, the queries are probably still going to take like it's doing that kind of analytics is of course going to take like 5 minutes, like maybe several hours, or even like a day or something in some cases. But that's why you have it in the data warehouse. And I think so if you're trying to do that personalized stuff, you might like update the data like once a day or something. There's approaches for trying to do more real-time personalization, like with YouTube, how if you like just watched a video about some new movie that came out like Dune, and then you go back to your homepage, it might show you a bunch of other clips for that movie Dune. And so there's tricks for making that work, but that's a lot more of you're getting into like MLE topics. That's so personalization is an MLE topic. There's some good books for that, like I think it's Kang Bam has a good book on that. Alex Shu actually now has a new ML system design book. I still have not had a chance to go through it a ton, but that is out there. I think there's also, God, what was the name of that other person? Chip Hoyan. That was it. There's another person that's kind of famous is Chip Hoyan is another big name in that world of stuff. But that's MLE, and that has a whole world of spice to it that I've kind of gone into in some other videos. Yeah, but just know that it's you usually will leverage a data warehouse for pulling in that other data. You wouldn't be storing that data on the way. You would not want to have that over along this path getting passed in. It would already be there from previous listens and stuff. So it would be in there from other requests, other services getting dumped into the data warehouse and not on this hot path. Yeah. Okay. Back to my thing here. I don't want to say 50 on this. I know that SkylaDB, like Discord's able to get away with just 72 machines there. So I'm going to treat it like this is what we're going to be doing. We're going to say that it's doing 2K transactions per machine, and it's only treat it like 10K writes. And so then that would be 5 machines, but again, we're doing it per region. And so we're doing 10K writes. We're going to split it over the 3 regions. And so then each region is going to have 4K to 5K writes at peak. Which would be 2 to 3 machines. You would want it to be able to comfortably handle stuff if one of the machines malfunctions. So you do n+1, and here, so n would be 3. So n equals 3, and so we want n+1 is 4. So we want 4 machines per region, and that is in 3 regions. Yeah, okay. I'm kind of happy with that estimate over there. And then in the real world, you figure that out with monitoring and metrics for figuring out what the actual peak number of transactions that a machine can handle. I was ballparking the 2K transactions per machine. You would actually determine that experimentally. There's even tools for doing that at Amazon. Yeah. I think I've handled everything that I wanted. So I did load balancers, I did machine count estimates. CDNs, we don't need that here. Oh, partitioning keys and stuff. Well, this one doesn't have any data stores. I mean, we can do that for. So I think here I can do it for my naive approaches. So I would do partitioning key for that, sort key for that. Redis would be an interesting one for that. So you would have, this is the key. So for Redis, the key is the song ID and the hourly timestamp bucket, and then the value counter CRDT. Okay. That is the secondary indices. I've gone over DB schemas. I went over that. I did machine count estimates. I think we can call it a day. Are there any questions before we wrap up the stream? Okay, I don't see any questions, so you guys can feel free to drop off. Thanks for joining me. Thanks for watching. I hope you guys enjoyed watching and that you learned something from this. I will put the diagram and the text file in a pinned comment below the video. Thanks again for watching. I'll let you guys go. See ya.